Thanks very much, Steve. Just turn that down, that's a bit. And thanks to the organisers for putting all this together. Sorry, second. Is that better? Yeah, I was interested to find from Steve over lunch that it's the students who select the people that come to talk, and now I feel the pressure that the student or students that sort of put their name forward are sort of going to be thinking, please do a decent job, or everyone's going to be saying, who decided to invite this Baggaley bloke to come and bore us for nearly an hour? So yeah, my name is Andrew Baggaley. I've come from Newcastle University to talk to you today. And for once, we have these kind of corporate images, as I'm sure Leeds does, that we're asked to use on our slides, and it never normally looks like this, but today, for once, it actually did, and it's a nice day down here. So let me just make that laser pointer. So my talk, when I got invited and asked to submit an abstract, I just dumped in a paper, but I really don't intend to kind of talk too much through the science of that particular paper, because I don't think that is what this symposium is about, but really to give an introduction to the topic and make sure that if any of you are at a seminar or at a conference where quantum fluids are discussed, you at least have a bit of an insight into what is meant by a quantum fluid and some of the unique properties of what happens when quantum mechanics constrains fluid motion. So, previous speaker said that fluid dynamics is a good excuse to show pretty pictures, and so this is my attempt. And just a reminder, I'm sure we're all familiar with both the concept of classical vorticity, but also the fact that its scale is not constrained by anything apart from the system size. So if we're in effectively an infinite system, we can have rotational motion on the scale of kiloparsecs. If we're constrained by the size of the Earth, we can have rotational motion with hurricanes of the order of hundreds of kilometers, down to tornadoes, down to my favorite example of this incredibly lazy cup that I presume has some sort of propeller on the bottom, so that if stirring your tea or coffee is too much effort, you can push a button for $20 on Amazon and have the mug do it for you. But I keep thinking I should buy it because I've used this picture so many times that I probably owe them some money. Okay, so this is a classical picture. What happens when I lower the temperature? Well, for most substances, if I take my bottle of water and put it in a freezer or a system that will lower the temperature, the fluid dynamics doesn't get particularly interesting because this thing solidifies, right? But as quantum mechanics was emerging in the early 20th century, it was realized first by an Indian theoretical physicist, Bose, who then wrote to Einstein, that if there was a way to stop a gas freezing by keeping the density, the particle density of the gas very, very low so that solidification couldn't happen, you could find a new state of matter where quantum mechanics would manifest on a macroscopic scale. And the mathematics are a little bit more complicated than the cartoon picture that I'll present. But if you've done any undergraduate theoretical physics or have an interest in popular physics, you might have met the concept of wave-particle duality, the idea of the de Broglie wavelength, or that subatomic particles can have a particle-like nature or a wave-like nature. And what really distinguishes between the two is the wavelength of the particle and how that relates to the separation between that particle and other particles. If the wavelength of the individual particle is very, very small compared to the separation, then we can think of them as point-like objects, like the gas in this room, or like the molecules in my bottle of water, that they're moving around, they're colliding in a classical picture like billiard balls and interacting. But quantum mechanics is really only taking place or constraining things within the molecule, within the atom. But we know from elementary quantum mechanics that the particle wavelength, I'm sorry, I'm using my mouse on the wrong screen, that the particle wavelength is related to the momentum of the particle. And if we cool the system down, that will lower the momentum of all the particles, and therefore the wavelength will increase. And if I can do this in a way that keeps the number of atoms in my system the same, the separation between the atoms is just to do with the volume of the container and the number of atoms. So that doesn't change, and I can reach a state where the de Broglie wavelength of particles becomes comparable or larger to the particle separation. And that means that quantum mechanics starts to take place on a larger scale, above the scale of individual particles. And if I can do that in a fluid, in a gas, which is a system that I'll talk about first, then I can have fluid mechanics, fluid dynamics in these systems that's constrained by quantum mechanics. So this is this cartoon, and I found a few years ago that the CNRS had paid some people, some cartoonists, to put together a really nice video just showing this, and it's going to do a far better job of this than I could ever do. So I'll play this for a minute, describing what I said. So we've got oh, sorry. Yeah, I can do it. I'm just forgetting what I need to do. Let's start again. What we're seeing is that cartoon picture of the wavelengths becoming larger as I cool the system. And then we see a sort of superatom formed. Quantum mechanics applying over the scale of this entire system. Now, one slight detail, I really don't want to get too technical with this talk, but you noticed here that it mentioned bosons at some point. So this can only occur in systems of bosons, where particles can take the same energy level, which is why electrons in shells of atoms don't collapse, because they can't fall into the same energy state. It can also apply to composite bosons, so atoms like helium, which are made up of subatomic particles whose spin adds up to an integer value. Okay, now, suppose Einstein put this idea forward. Let me jump back to my talk. And it took, order of what, 90 years for people to experimentally be able to realize this in the lab. But in the 90s, people started to realize using lasers that you could cool down element 1 alkali metal atoms easily to very, very low. I say easily, but could be done to very, very low temperatures and create these BCs. And they were awarded the Nobel Prize. And now it's a routine thing to create BCs. Experimental. So my talk, some of the videos that I've got have not played on this machine, so we'll have to jump back a little bit every now and again. Now we can also see quantum fluids in helium, which I sort of briefly mentioned as a composite boson. So helium is the one example of a fluid that if I take, this is obviously not a bottle of helium, if I took a bottle of helium gas at room temperature and could cool it down to as close to absolute zero as I could get, helium would remain. So helium is a system as well that can be studied as a quantum fluid. Why helium remains a liquid at zero temperature and the physics of helium and how it differs from a Bose-Einstein condensate is sort of beyond the scope of this talk. But we can treat these two from a fluid dynamics point of view. We can treat these two systems fairly similarly. There are some differences that I'll talk about. So helium was first liquefied in the very early 20th century by Camerlinger Ons, who's the chap sat, sorry, I keep forgetting about two different screens, by Camerlinger Ons, sat here, and his group in Leiden, and they were competing with James Dewar to liquefy the remaining gases that had not been liquefied, and he made a startling discovery that if he placed a mercury wire in liquid helium at very low temperatures, a current could flow without resistance. So he got the Nobel Prize for discovering superconductivity, but unbeknownst to him, had also discovered superfluidity. And these two phenomena are related. Now, one of the things that we'll find as we look at quantum fluids is if we stir these systems, quantum mechanics will constrain the fluid motion. And the most obvious thing, and the one thing that I want you to take away from this talk, is how it constrains rotation. So in a classical fluid, we show these pictures to argue that rotational motion, the size of it is only constrained by the container, effectively. In a superfluid, like helium and like Bose-Einstein condensates, rotational motions are constrained to incredibly thin atomic quantized vortices. And the circulation around these vortices is fixed. So, like many things in quantum mechanics, there's a quantization and circulation becomes quantized. And so it might be appealing to think that the system is simple, because rather than having vorticity that can take a large hierarchy of scales, vorticity becomes constrained to these effectively line defects. And that's true in helium, and it's true in atomic Bose-Einstein condensates. The pictures that I'm showing here, and I'll come back to these pictures, are from an experimental setup in helium that was done in the US in the early 2000s. And the dots that you see are little hydrogen snowballs. So you cool down your helium system, shake it around a bit, and stirring it creates some motion. And these motion are manifested through these quantized vortices, just like motion in a classical fluid is built through classical vortices typically. And it becomes dressed with these very, very small hydrogen snowballs, which are sucked in to the cores of these vortices. And the only difference between the top and bottom is just the different number of particles, different particle density of these hydrogen snowballs. So in the bottom, it's incredibly dense, and so you can really see these small line defects. Now, typically, visualization is a really difficult thing in quantum fluids, and I'll come back to that idea in a second. So now we can ask a really sort of toy example of, if we have this quantization of vorticity, how did it affect really, really simple fluid motion? And rotation might not be the simplest fluid motion, but it's one of them, right? So if I take the water in this bottle and I rotate it, put it on a turntable or whatever I do, and I come back, if I constantly rotate this, and come back at some point later and make some measurements, then I'd expect to find the fluid in this bottle rotating as a solid body. If I take helium or a Bose-Einstein condensate and rotate it, what happens? It should rotate like a solid body. But I also know that physically vorticity is constrained to these very thin quantized vortices. So how does the system sort itself out? Well, what appears as you rotate these systems is they become threaded with an array of these quantized vortices. And the number of them has to match the rotation rate so that you match classical solid body rotation. And if I blur my vision, take glasses off or whatever, and step back a scale from the scale of the individual vortices, whose velocity field goes around 1 over r, but I coarse grain and average over many vortices. Oh, sorry. Just shout at me. I clearly can't cope with 2 screens. Yeah, so there's my rotating bucket, and it becomes threaded with, I'll try again, with these quantized vortices. Around these vortices, there's an irrotational 1 over r flow. But if I take a coarse grain picture over many of these vortices, I recover solid body rotation. And so these systems are a little bit weird in comparison to classical fluids. This was first proposed by Feynman and Onsager. As I say, the sort of experimental verification typically comes later with quantum fluids, but this is an image from the 90s where people rotated a Bose-Einstein condensate and imaged it optically And all you're seeing here is the gas density. Where it's bright, there are lots of atoms. Where it's dark, there are very few or zero atoms. And these holes are the cores of the vortices, where there isn't any gas. And the number that you find as you increase the rotation rate or system size matches what you would expect to see classically. Okay, so rotation is one thing that you can look at in these systems. You can also excite them a bit more vigorously. So you can stir them in a more complex way and study more disordered fluid motion in these systems. And ultimately, you can get to turbulence. And it was Feynman who first became interested in this and proposed the idea that if you could have turbulence in these quantum fluids, it would manifest itself as a tangle. These very thin, almost one-dimensional lines. So think of taking a knitting ball or whatever it is and untangling it and stirring it up. This tangled disorder of line defects is how we think turbulence in a quantum fluid manifests itself. So where can you see these if you want to study them? So there are really two systems on Earth and one in the sky that you can look at. The first of those is helium, which, as I say, dates back to 1910s and is the oldest system that's looked at. And here you can see a helium cryostat. This blue part is where all the action is taking place. And the first thing that might jump out is that it's really difficult to see what's going on inside there. And so it wasn't really until the early 2000s that it was possible to engineer these systems with windows. And windows allow you to shine laser beams in, and laser beams allow you to start to do this visualization. And these are the first images that started to be seen of turbulence or fluid dynamics in a quantum system. This is a rotating array, again dressed with these particles, and you see forming this lattice. And here are more disordered systems. We'll look at some movies of these as we talk. There is also a second way of visualizing, which I won't go into that now, just in the interest of time. And there's also atomic BECs. So these are these clouds of typically period 1 atoms, sodium, rubidium, which you cool down as a very, very rarefied gas. And the experiments here look like this. They look like an optical experiment because they are. They take place on huge optical tables, and all you see is a mess of laser beams. And visualization is very, very difficult. It's almost like, if there's any people doing projects in astrophysics, it's a very similar problem that you basically see column integrated quantities of things like density fields integrated through line of sight. So visualizing three-dimensional tangles or disorder is quite difficult, but you can excite these systems in very controlled ways. So this is a numerical simulation of an experiment that took place about a decade ago, where you take a container of these gases and you slosh it backwards and forwards. Because these things are incredibly compressible, sloshing it backwards and forwards can break locally at the speed of sound, and you can create a tangle of these quantized vortices and study them. So in the lab, we've got two systems which share this phenomena of quantization of vorticity, but are quite different in the fact that one of them typically take place in much larger experiments, in helium, which could be the order of a meter, and they're incompressible, and we don't have a huge control over the parameters. And the other one is in atomic condensates, which are much, much smaller, so typically micrometers across. You can only simulate or experimentally have a small number of vortices, but we can control geometry. We can look at these systems in 1 dimension, 2 dimension, and we can tune interactions to really play with the fluid dynamics in these systems. And it's potentially Bose-Einstein condensates, which are a little bit more interesting from an applications point of view, because fluid motion in these systems could be used for sensor applications. So to develop next generation detectors of acceleration or whatever in devices. It could be fluid motion in these systems down the line. The other place where we see quantum fluids that motivates their study is in astrophysics and in neutron stars. So the physics of neutron stars is very complicated, is not my expertise, but this is a cartoon picture. Neutron stars are objects which essentially have all of physics condensed down into an object of the order of kilometers across. There's huge gravitation, there's particle physics deep within the core of neutron stars with potential quark stars, there's magnetic fields, there's a complex lattice crust in the stars that people study. But within the star, it's believed that there's a layer, outer core part of neutrons which are both superfluid and superconducting. The protons are superconducting. And that forms a superfluid system that people actively study and use some of the techniques that I'll describe shortly. Where do we see evidence of superfluidity in neutron stars? Observing things in neutron stars is basically all done from radiation emissions as these stars spin. And the vast majority of neutron stars are pulsars, so they're like lighthouses that from their poles emit radiation that you can observe. And so you can track their rotational speed or the period of their rotation. And in time, what you see is them slowing down. I mentioned these stars are magnetic, so they're subject to magnetic braking. Essentially, the interaction of the magnetic field with charged particles is a way for the star to transport angular momentum away and slow down. But what we see, this is not the world's greatest picture, I'm afraid, but what we see if we look at this curve of the rotational period as a function of time going along the x-axis, we see in general the star spinning down as the rotational period gets slower. But every now and again we see these jolts. These are termed glitches. And it's believed that this is evidence of superfluidity. And this is the interaction of this continuum-like core, continuum-like crust with this superfluid interior. So here's a sort of cartoon picture. And the standard argument is that the crust, where the magnetic field is tied to, is slowly spinning down. The superfluid doesn't know about this spin down. So it remains rotating faster than this crust. And because this crust has got these disturbances that the superfluid sees, this lattice creates little edges that the superfluid can see. There is some coupling. And every now and again, the superfluid gets dramatically braked by this crust and can transfer some angular momentum back to the crust and be spun back up, resulting in these brief accelerations that you see in the star before it relaxes. And we've started to do some work on that. This works. Let's come up before I start talking through it. So this is the two-dimensional numerical simulation of an equation that I'll talk you through shortly. So the mathematics we can get into, but it's a system of vortices, so point vortices almost, which are visualized through these little red dots, and pinning sites. So these pinning sites are meant to mimic the lattice-like crust of the neutron star. And what we're going to do is the entire system is rotating at a steady rotation rate, and then we're slowly going to break these pinning sites. We're slowly going to slow them down as if to mimic the magnetic braking that the crust will see. And what we'll start to see is these vortices move outwards. I'll play this a couple of times. But as these vortices move outwards, the superfluid is not spinning down. It's not until they can leave the system through the boundaries and transfer this angular momentum to the crust. And so we're very, very early into this project. But what you see if you look at things like the angular momentum, which I plot here, the angular momentum of the superfluid, you can see these large-scale drops that come as collectively some mechanism for a number of vortices to leave the system. And in a real neutron star, this would be billions of vortices simultaneously transferring their angular momentum to the crust. This is some complex collective phenomenon that we really don't understand. Okay, so what's the mathematics that I was simulating there? I probably should have had these the other way around. So the mathematics that I'm not going to derive but present to you is really not valid for neutron stars or even for superfluid helium, but can be derived fairly rigorously for these atomic condensates that I talked about. And the equation that governs their motion is what's called the Gross-Patievsky equation. And if you've met something like the Schrödinger equation as an undergraduate, if you ignore this interaction term here, this nonlinear term, then we have a Schrödinger equation, this term here, making it a nonlinear Schrödinger equation. And it's this term here that's responsible for atom-atom interactions. So what does this look like? Can we give this a fluid dynamics? Can we think of this in the context of fluid dynamics? Because this is a fluid dynamics symposium. What we can do is, psi, I should have mentioned, is a complex scalar field. So what we can do is we can substitute in for this complex variable an amplitude and a phase, and perform what's called a Madelung transformation. And from that, we find trapped within this nonlinear Schrödinger equation is a continuity equation and something, if we ignore this final term, effectively an Euler equation with this difficult final term. And we can attribute physical quantities to this mathematical variable psi, so we can attribute a density to its norm squared, the velocity field through a gradient of a phase, so we recover an irrotational velocity field. We can talk about a pressure field, and we also have this final complicated term here, which is called the quantum stress term. And typically, and I've been guilty of this in things like grant applications, we say that in quantum fluids, this constraint of fluid motion, making vorticity constrained to these thin lines and the circulation be fixed, simplifies things. And so quantum fluids are perhaps an easier way to understand classical fluid dynamics and classical turbulence. I don't entirely buy that, because if I replace this with a Navier-Stokes equation, we at least rigorously understand dissipation in a Navier-Stokes fluid, and we don't understand rigorously even dissipation in these systems. We've got pictures for how dissipation will work, but I don't think it's fair to say that these systems are very simple. That quantum pressure term does lots of things, but the most interesting thing from a fluid dynamics point of view that I want to talk about today is it allows vortex reconnection. So if we go back to the mathematics, if we remove this term here, then we've got an Euler equation, and so topological properties of the flow are invariant. So if I've got linked vortex rings, they have to remain linked forever. What this quantum pressure term allows is various physical effects, but most prominent being vortex reconnection. So it allows a topological rearranging of the system. It allows vortices that come very close to one another to short circuit, to rearrange, to minimize the energy. If people are doing topics in MHD we can draw an analogue between the reconnection of these quantized vortices and reconnections in MHD, or indeed reconnections of classical vortices as well. So these are some movies that I think hopefully should play. Perhaps not. What this movie I will describe would have showed is a vortex line moving towards the other vortex line, then reconnecting, and then the two halves, so a red part and a blue part, moving away in one direction, and another blue and red part moving in another direction. And what this movie would have shown is the ring moving towards the line, reconnecting with the line, interacting, and a small ring pinching. And this is one of the ways that energy can be transferred from larger scales to smaller scales in quantum fluids as we start to think about turbulence in these systems. This movie also won't play. What this shows is a slice through in the center of me during a reconnection of the density field. And what we would see as these vortices move towards each other and reconnect. So the setup here is a vortex-anti-vortex that will move and undergo, if you're familiar with the Crow instability, if you've ever seen trailing vortices behind an aeroplane, it would drive a reconnection. And in the density field behind it, we would see a rarefaction pulse as some energy from some incompressible energy associated with vortices is transferred to compressible energy. So this is also another movie that won't play. Let's see if I can just. Oh, maybe it does play. Apologies. I'll not go back to the other ones just in the interest of time, but this really sums things up. This is an experimental observation for the first time of reconnections. So this is these helium experiments that I showed you previously, where visualization is done through these hydrogen particles. And we see vortices interact with one another and reconnect. So I'll just play that one more time. So this is the sort of phenomena that we would have seen in the numerical simulations of two vortices coming, interacting, and then moving apart from one another. Okay. Okay, so I know that no one on the CDT is doing quantum fluids, so I'll have a quick summary so that at least take something away from this talk, and then if we've got time, I'll start to get into the sort of science of what I want to present. So in quantum fluids, quantum mechanics constrains the fluid motion. And the most obvious way is through this quantization of vorticity, both in terms of the size of these vortices and in terms of circulation. If we rotate these systems, we see lattices. If we stir them in a more complex way, we can get turbulence, and that turbulence comes through a tangle of vortices. And I mention they're randomized because the topology of this tangle is something that I'll discuss as we get into the science a bit more. We can study them really on Earth in two distinct systems: an incompressible large-scale system in helium, and in much smaller but very, very compressible Bose-Einstein condensates. And we think we observe superfluidity in neutron stars. That is a much more complicated system, though. The same thing. Sorry, I need a sheet draping over this other screen. Other things that I've not discussed, so you can see there's a lot of other things in quantum fluids that I've really not provided introduction to. So we can have waves, and I think maybe you saw that in that movie that I presented, that when these vortices reconnected, you could see ripples along these waves. So people who are interested in waves, and particularly wave turbulence, have studied these systems. In the compressible Bose-Einstein condensates, we can look at bonding interactions between the compressible waves. Within a neutron star, there's a superconducting proton flux tubes, and they interact with these quantized vortices. It's a very complex system. If anyone has met a classical ferrofluid, so these typically black suspensions of ferroparticles within a fluid, and you bring a magnet and you see this Rosenweig instability, this hedgehog-like spiky instability. There are certain atomic species that have dipolar magnetic interactions that can behave like quantum analogues of dipolar systems. I didn't mention finite temperature effects, and I'll briefly discuss that shortly. Boundary conditions was something that I stayed completely away from because it's much more complicated than the classical, slick boundaries, or I might have if I'm trying to understand a classical hydrodynamic experiment. I can have solitons in these systems. In one dimension, these solitons are stable. In higher dimensions, these solitons are unstable and break apart into vortices. And I can also study two-dimensional fluid dynamics in these systems. And if you've studied point vortices through complex analysis, this classic undergraduate fluid mechanics, quantum fluids are about as close a system as you could get to being a candidate for using point vortex theory. So what I'll now do for the remaining time I'm meant to finish, Steve? Yeah. Is to focus on turbulence in superfluid helium. And I won't talk for ages. What I mentioned a couple of slides ago, if I go back, was the idea that turbulence in these systems is a random tangle of these things. And what I want to talk about in the remaining just couple of minutes is how I could have a random tangle of quantized vortices that give me something that looks like a classical system. So I've skipped through a few slides. If you're familiar with standard turbulence theory, great. If you're not, sorry, I've not got time. Imagine if I stir a classical fluid in 3 dimensions, then I'm expecting a hierarchy of scales. If I stir with my arms and inject some energy at a wavelength of, say, my arm, as turbulence develops, I'm expecting a forward cascade of energy and energy to be distributed through rotational motions of different scales. If I take a helium experiment, and this is a schematic of it's effectively a superfluid wind tunnel, what I can do is measure things like the energy spectrum and higher order statistics like third order structure functions, both above and below where the system is superfluid. Above where the system is a superfluid is shown in a red line. Below where the system is a superfluid is shown in a blue line. And what I see is all the predictions from classical turbulence theory apply when the system is a classical fluid, as they should, but also occur when the system is a superfluid. How can this be the case? Well, it's that the structure, the topology of this tangle is a bit more complicated than Feynman perhaps first suggested. That it's not just a random tangle of quantized vortices, but there's some self-organization. So this is a very early numerical simulation of the Navier-Stokes equation that was published in the 1990s that shows isosurfaces of the vorticity field. And what you see are these intense vortical structures, typical vortical works. And what we've started to think recently in the last decade or so in quantum fluids is the way that they can mimic classical fluids in terms of their energy spectrum and allow there to be a hierarchy of scales, even if vorticity is constrained in terms of circulation size, is that there's some self-organization into a non-trivial topology. That you can have bundles of these vortices that can form and interact. And the science that I was going to talk about in the abstract was looking at the interaction of these bundles, but I think it was more important to sort of set the scene. So that's where I'll finish. Sorry, I've broken my time, have I? But I've got a couple of minutes. Okay. What I'll do is try to present some evidence that these bundles do exist. And I won't turn to numerics or anything like that because that's not as convincing as experimental evidence. Sorry, I don't know if I've just done that a bit too quick and the system is frozen. Sorry, the slide that I want isn't coming up. Yeah, in the slideshow I see one slide and on the screen. Have I broken it? Sorry. So we find numerical evidence if we do simulations, but much more convincingly seen this experimentally. And so this is another schematic of another experiment that was done in France in helium. The French love this von Karman system of counter-rotating French washing machine. They call it these counter-rotating propellers. They do it with everything. They do it with classical fluids, with MHD, and they've done it with superfluids. And this is a very large system, about an order of a meter, a cubic meter of liquid helium. And what they've got are pressure transducers within the system. And what they look at are time series of localized pressure. And what you see are these time series at different temperatures. And if we look at the lowest temperature, you see these very large negative deviations of the pressure. And if you look at the statistics of these time series, you see this strong deviation away from Gaussianity, these very negative pressure tails compared to relative pressure. And these are associated with these intense vortical tubes, which in a superfluid can only come if they're bundled together. And so this is the strongest evidence that we have outside of numerics that shows that there can be some self-organization, that when we stir these quantum fluids, the tangle is not quite as random as first suggested, but contains these bundles. Yeah, okay, and I think that's a nice place to finish.